Hello, and welcome to the Big Bang Kilonova Hypothesis vlog. My name is Stuart McLean, and I am both your host and progenitor of said hypothesis. In this particular episode, I want to start by discussing the new film that I released a couple of weeks ago. Essentially, I was going on holiday, and I wanted to show people on holiday what I was working on, and to find the episode, you can find it on my website, or you can just find it in it's the Big Bang Kilonova Hypothesis. The episode I've just simply called Anatomy, or rather, Anatomy of a Kilonova. The general idea is that fractal geometry is the cosmological principle, and self-similar patterns repeat irrespective of scale. So, in describing the Big Bang as coming from a kilonova, and the reason for describing it coming from a kilonova comes from the cosmological principle, where I'm saying self-similar patterns repeat irrespective of scale. This is the law of scale invariance in chaos theory. And at the heart of the Big Bang theory itself is the birth of our gravitational singularity. Now, in order to understand the birth of an unknowable gravitational singularity like the Big Bang, we need to understand how the birth process of what I would call a knowable, or at least observable, gravitational singularity being born in our universe. And there's two ways this can happen, or two ways a stellar black hole can be born. It can be born either in a hypernova, which is the core collapse of a massive star that is sufficiently massive and dense such that when its core collapses, it collapses down into giving birth to a new black hole. The other way is via a kilonova. A kilonova is the binary merger of two neutron stars. So a kilonova is the kilonovas, hypernovas, these are very general descriptions usually given to what are called transient events. Here on Earth, we see a bright flash or something, some gamma rays, and then it passes within a couple of days. And a kilonova is, as its name describes, it gives birth to short gamma ray bursts as opposed to long hyper gamma ray bursts, which occur in hypernovas. But the main thing about choosing a kilonova comes down to the large-scale anisotropies. So I switch back up here, and it more or less can be seen in a large-scale anisotropy. So you've got this large red spot. So just to show you where this data is coming from, this is the ESA Planck and enhanced anomalies, showing a not so isotropic universe with these large-scale anisotropies. This goes against the current standing cosmological principle, and hence why I would name a particular this. I'll just bring it up. So on this particular map versus this map, this is what I would call an ideological map that matches the cosmological principle that the universe is homogeneous and isotropic at sufficiently large enough scales. Whereas opposed to this map, this particular map shows these large scale temperature fluctuations that are seen across the microwave sky, whereas they kind of remove them here because no one's actually been able to explain them that yet. And one of the justifications that they take, one of the justifications that they said is that the universe is, at the larger scales, the universe is both homogeneous and isotropic. So this happening is, well, this is not actually part of the Big Bang. It's something else that's happening between us collecting the microwave data and filtering it out. I, on the other hand, will contest that these are actually part of a large scale, the actual microwave background sky, and the fact that it's being published by the ESA shows it is so. And but when put onto a Molly-Weld projection, so it's projected effectively this is what they call a Molly-Weld projection of a 2D of a spherical map, and so I've created a spherical viewer so that you can actually see it properly in 3 dimensions. And when you look at the sun towards the South Pole, we have this identifiable cold spot called the Eridanus supervoid, and this identifiable hot spot. So you've got 2 parts which they then form the large scale anisotropies. And the reason I say it's a kilonova is because gravitational waves of a kilonova effectively give rise to this birth of this new black hole. So that in a nutshell is the justification for me saying that in order to understand the Big Bang, we must understand the pattern of a kilonova in order to understand what caused in order to understand these large-scale anisotropies. I spent about 3 years when I first sort of started developing this idea, trying to think about it in every single possible way. And it took me a very long time to learn this one simple lesson. If a kilonova is doing it, or if a hypernova is doing it, then infer onto the pattern of the Big Bang in order to tell the story of the Big Bang. That, in a nutshell, is the simplicity of the Big Bang Kilonova Hypothesis. Study the birth of one gravitational singularity at one scale, because fractal geometry is a cosmological principle and self-similar patterns happen irrespective of scale, and infer it to the larger scale, namely the Big Bang, the birth of our universe. And that is exactly what I do in this film. That's its entire purpose. But in retrospect, I find there are 2 audiences that I want to try and communicate this to. One, a general audience, to anyone who wants to listen and learn about how scientific hypotheses are built. And the other one is the actual cosmologists. And I'm going to prioritize my communication towards cosmologists now, because that's where this idea needs to be shown. My basic intention, one of my basic intentions, of there are many, is like, I'm saying to cosmologists, you haven't thought about this idea. You haven't contemplated it. You haven't even considered it. I have. And here is my argument. So from the very beginning, I try to aim at people who are, so in actually making my film, I aim it at cosmologists, but at the same time, at each particular stage, I'm trying to explain or animate the principles behind what I'm actually saying. Trying to animate and explain so many new states of matter, electron degenerate material, neutron degenerate matter, quark, gluon plasma. These are new states of matter. And then there's condensed matter physics, which has many parallels with the internal workings of a neutron star. Well, that's the argument I along with many others, are putting down. They look to what's called condensed matter physics. And what's happening in condensed matter physics is, in a laboratory here on Earth, we cool things down to just below, just try to cool things down to the lowest possible temperature state, which is 0 Kelvin, or I think around about minus 273 Celsius, what we call absolute zero. Beyond this point of temperature, you can't go down any further, which is, I have many thoughts about that one, but leave that aside. I mean, it'll take one Scotsman to go after Kelvin. The problem I now have is, the argument I managed to put together here is, I'm just going to nickname it inflation killer. I'm just killer. There comes a point towards the end of this film where I've actually laid out all the parts, laid out everything, and I'm deploying my full argument that I now have. It answers all the questions for why inflation theory exists. So I'll just bring up cosmic inflation. So this is the standard model of cosmology. This is when people talk about the Big Bang theory in the current context, or when they're usually talking about this specific interpretation of the Big Bang, where back in the 1970s and the early 80s, there were a large number of problems in cosmology that had to be answered. First one was the flatness problem. And the flatness problem basically comes from astronomers have measured the shape of the universe from the cosmic microwave background sky. And just do a quick search for the word flat, because I know I've So there is this particular paper, a flat universe from high-resolution maps of the cosmic microwave background radiation. So effectively, cosmologists have measured the shape of the universe using the microwave background radiation and by other means, and they found a universe that is essentially flat. But then, in the Planck evidence, we find a universe for evidence for a closed universe and a possible crisis in cosmology. The simple explanation or the whole idea of that that I base my that I base it or that I base my idea around is the idea of the expansion of an entrapped volume of space-time. So here's the animation of a new black hole is born with being fed by an accretion disk, and you get these two entrapped manifolds of space-time, or what is the electromagnetic field, effectively being ripped in two, and within the blisters of that, two new entrapped manifolds emerge. So one of the words, I mean, that's one of the words, like one of the phrases I seem to keep using, entrapped manifold of space-time. So my whole idea in being framed in terms of general relativity comes from what is known as the extended solution of the Kerr metric. Kerr metric is a solution of general relativity when you consider rotation, and so this is essentially one of the foundational building blocks, the foundations upon which I am building my hypothesis. In putting it in terms of more in terms of that are more better for cosmology, because this is actually a local solution. And from the point of view of an observer in the superverse, it is a local solution. But from our point of view, being born entrapped inside one of these two new entrapped manifolds, from our point of view, we would use what's called a cosmological metric, such as the FLWR metric, the Friedman-Lemaitre Walker-Robertson metric. But in terms of like phrasing it from an observer here, I particularly lean into the work of Nikodem Pompolomsky, a Polish theoretical physicist whose theoretical work and mathematical framework gives huge amount of it gives mathematical formulation to everything I'm trying to say. But then again, there's quite a lot of things that are giving mathematical formulation within the annals of physics. This diagram being primary. Another factor is this is the conformal diagram coming from Penrose, but one of the actual manifestations I will now argue of self-similar patterns repeat themselves irrespective of scale. The real full manifestation of this is an argument is essentially what's known as ER equals EPR, and this is how the top universities, the staff. So this is essentially coming from Oxford, Stanford, MIT. I mean, it's coming from Oxford, Cambridge. It's Penrose conformal diagrams. Conformal essentially just means angles are always preserved at every single moment of scale. Now that in itself is, if I could nail down the geometry or causality, it is down to it being conformal. Conformal means that that it is that local angles are preserved irrespective of scale. And so that's why this works, because this is a much smaller scale than this universe. This, in my model, is what they call a subverse, or our universe is a subverse of the superverse. What is a superverse? What's a subverse? Well, if this is the black hole that gave birth to our universe, then this down here is a superverse. This is a much larger reality. Yeah. Okay, to show this principle, I've got a Mandelbrot set here. And so as we zoom into the Mandelbrot set, you're going to see the same pattern that we saw that we see here. We're going to see this being replicated at multiple scales, irrespective of scale. So one of the things I'm narrowing in on is local angles are preserved irrespective of scale. More generally, this is called conformal field theory. And so here we have the Mandelbrot set coming in. And so if we imagined this Mandelbrot set shape here, this void, black, and trapped here, we imagine that is our universe. And then we zoom back out, then this would be the equivalent of the superverse. Of course, I particularly, in visualizing it as an observer, watching the black hole being born, if we could see these entrapped manifolds, we would see the inflation of these new entrapped manifolds. And that is essentially what the mathematics of general relativity is telling us. After 100 years of studying general relativity, this is the map of the multiverse. And this is my interpretation of this map. You have one entrapped manifold of space-time being born here, and another entrapped manifold here. So an entrapped manifold essentially means light cannot not escape it. And if we go back here, light cannot escape a black hole. Black hole is itself entrapped. And the light passes on down through the wormhole, becoming entrapped again here. So where the sharp purple boundaries are is another region of entrapment. And then the light travels on into the white hole, which is simply a black hole working in the complete reverse. And then out into one of the two new parallel universes, or these two new entrapped manifolds of space-time. So this is what general relativity is telling us. This is my interpretation of it. And that's the idea. That's it. Everything else comes down to that. But no, not just everything, because I'm studying the entire kilonova. I'm studying what's actually happening. And one of the things that's happening, just reverse this a wee bit, is that it's getting imprinted by the gravitational waves of a kilonova. As the two neutron stars swirl into each other, they give off a gravitational wave. They give off these gravitational waves. I'm just stopping because I'm really coming right back to inflation in theory. In the 1970s and 80s, cosmologists were faced with a number of problems. One of them was the flatness problem. And that has been seen. So this is a matter of observed reality, where we've measured the angle, we've measured the geometry and the shape of space-time from the cosmic microwave background, and it shows that the universe is flat, and many other things have been indicating why they're flat. Coming back to this idea of entrapped space-time, so where is this expanding? Well, I say it's expanding into the spatial volume occupied by the superverse, and the region around the kilonova is most likely going to be vacuum, like the great majority of our universe is just vacuum space. It's not the only time you actually get curvature in our universe is when you've got a concentration of mass energy density. That's general relativity 101. So as our universe expands, as it is born and expands, it is expanding into the spatial volume of vacuum, the vacuum of the superverse. There's vacuum, but because fractal geometry is a cosmological principle, any laws of physics within our universe, specifically general relativity, and especially general relativity, has its own expression within the spatial volume of the superverse, which is to imply if there's any mass energy density, say if there was an object of the superverse here, it would cause the curvature of this entrapped manifold to flow around it or envelop it, as is the case, and this is one of the kind of first arguments that I kind of laid out in giving form to the idea of the superverse. When I first wrote this, I didn't even coin the term superverse. Now, 4 years later, superverse is really simple. It's our universe, exact same laws of physics, but at a much, much, much bigger scale. And the scale of it can be expressed by this large spherical void. So this is an object of the superverse around which our universe has flown. Sorry, let's find what is here. So here's flat shape of the universe, an object of the superverse impinges onto it, and our universe comes to envelop and entrap it. Or another way of expressing it is using fluid mechanics. The equations describing a perfect fluid are an exact solution of general relativity. So, in describing our universe as like a superfluid, and there's many theories that are like that too. Most famous fictional one of that being Sheldon Cooper and Leonard's description of a superfluid universe from the TV sitcom The Big Bang Theory. As a real life Sheldon Cooper. I'm not Sheldon. I'm not. I imagine there are people who have spent their lives looking at physics and have attended all the special classes that you need to go through in order to just understand everything about the standard model of physics, such that you're able to actually contribute to any mathematical descriptions of frontiers of said fields. Usually, when I'm getting the feeling when cosmologists get together, they just start showing off, or theoretical cosmologists, they just start showing off all their mathematics and they're just really pure mathematicians who've decided to come in after physicists have given up on any idea of objective reality. And the whole notion of physicists giving up on objective reality really came down to this ER equals EPR, which flowed from conformal field theory, and effectively, yeah, my original point was to show that two entangled black holes, the mathematics describing this, are an exact match to that of quantum entanglement. Self-similar patterns, because fractal geometry is a cosmological principle, repeat irrespective of scale, and this is the ultimate expression of it. After 100 years of studying general relativity, this is the frontier of where we're at. And this is no longer a mathematical conjecture. It is backed up by experimental evidence, the subject of which I talked about in a previous vlog, where Google AI, where Google's quantum sycamore chip was used to create a traversable quantum wormhole. So they sent information in at this end, and they had to come out at the other end. They created a wormhole through across the width of the sycamore the sycamore CPU's die. And that doesn't even work because I'm thinking about silicon dies and quantum processor is quite a lot different. It's not silicon chips anymore. It's condensed matter physics and liquid helium, which is kind of what I'm pointing towards as going, which is another argument that I kind of try to make in this film, showing off Martin Tajmer's experiment showing gravitational frame dragging within a lab. That alone is like, I think I really stopped talking to people about all this sort of stuff now, or just bring up in general casual. You can't have a casual conversation about the beginning of the universe. Believe me, I've tried. You look at people's eyes just go immediately blank, and cosmology is a very specialized field. I spent 7 years studying. I'm a complete geek on this stuff now, so just randomly trying to explain it to even other people or anyone, other scientists, is like, yeah, this is not my field. And ultimately, I'm ultimately, with following through on my principle that one needs to understand everything about a kilonova in order to understand the Big Bang. Well, in doing that, I've essentially come up with an argument that I'm calling inflation killer. One of those being answering the question of why is the universe flat? The universe is flat because as we expand into the superverse, I always like my animations and background. So yeah, here we are. As we expand into the superverse, so as this expands, it's the volume here is vacuum. So it's expanding into the vacuum of the superverse, because the vacuum of the superverse is flat by the special relativity of the superverse's version of special relativity. Then it implies, well, the shape of space-time the shape of space-time in our universe, when there's no mass energy density, is flat. The shape of the superverse's structure is itself flat, with one exception. Though not animated here, the exception is the gravitational waves. Though it is kind of animated because it bounces down onto the gravitational waves, and that creates the large-scale anisotropy imprint in the southern hemisphere. So because we're expanding to the volume of the superverse, as the two rebound off each other. So you've got the shape here of the kilonova waves, but because the universe itself is expanding into the flat nothingness of the superverse, which itself is flat, then that gives shape to our universe as being flat. But the other important point is that I also say it is entrapped. And my evidence, and the paper I particularly cite is this one, the Planck evidence. Planck here being this Planck, the Planck satellite mission, and the evidence that shows that for closed universe. So we've got this. So it's both closed and flat. Well, it's an entrapped manifold of space-time, like being expanded out into the volume of the superverse, which is itself flat. But at the end of the day, like a balloon, it is entrapped. The nozzle of the balloon being the white hole. Coming back to cosmic inflation, it was developed to answer that problem. Why is the universe flat? Why do we see this? And it was developed to answer that specific problem. It's a theory based on quantum field theory, and it describes the creation of what is they call the inflationary field, which I'll just bring up a line to see the. So this is the standard one you'll see. I'm finding one with the actual specifics of inflation in it. So this has got. I mean, this one is just like one word: inflation. unification of usually this is termed in quantum field theory. That's the one I'm looking for. I just want the picture. Open. Yeah, so this essentially is the inflation model, or when we're talking about inflation theory, we're particularly talking about the quantum inflation or Landau CDM model. This is the hypothesis that I've got to overturn. And the reason why this hypothesis exists is to answer that specific problem. That is one of the problems it tackles. And here it basically says, start out with a point singularity of infinite density. How it came into existence is talk about M brains crashing together, or well, there's so many mathematical descriptions. Everyone's got their own cosmological model in theoretical cosmology that just as long as it's based on inflation theory, just don't question inflation theory. If you question inflation theory, you're going to be booted out of cosmology. And that's why the universities are a bunch of losers. That's my statement on it. I win, you're a loss. The way it answers this, of how a point singularity of infinite density goes from here to here. What's happening from here to here is that point is expanding faster than the speed of light, which is, I find it very curious. I want to know why do you need this description? Why do you need this faster than light expansion? One of them is really to describe why this side of the universe and this side of the universe, which fly apart and expand and expand and expand and expand and expand, come to look the same. And it's saying this part up here is going to be equal to this part down here, and it does, and it's using this description of this one inflationary, this scalar field, which you call the inflationary field. Effectively causes this fast light expansion, and then I'll probably talk about the Higgs mechanism later, because this part I was like, well, in my model, I've got my defined place where I've got my faster than light, or where the flow of space-time is faster than the speed of light by definition of a black hole, of a white hole. Below the black hole's event horizon, the flow of space-time is moving faster than the speed of light. It's why light becomes entrapped and you get this new entrapped manifold. And then there's the same logic here. The geometry of causality for forces has these specific barriers. And then you have this anti-horizon here. At this anti-horizon here, things go from being where the flow of space-time is faster than the speed of light. It now becomes the flow of space-time out into this new universe, into the new parallel universe, is slower than the speed of light by definition of what these parallel anti-horizon and anti-horizon are, just by definition of what the event horizon and parallel event horizon of a black hole are. This is where it does differ, because I'm saying this is coming from one universe, but I think this is one side of the electromagnetic field. This is the other side of the electromagnetic field that gets entrapped. I've got some really lovely animation for showing all this entrapment. So as the two neutron stars collide, they shatter off. Quark gluon plasma is released. Quark gluon plasma coming from the neutron star's core. In inflation theory, go back. At this point here, the only point where you find quark gluon plasma is here. Or hopefully they're trying to recreate it within the Large Hadron Collider at CERN in Geneva. Yeah. There's another argument that comes from using a Kilonova binary neutron star merger. Well, heart of each neutron star is a core or quark gluon plasma. There's been so many discoveries about strange stars. Stars made up of strange quarks as a new candidate that's supposedly lighter than what a neutron star can be theoretically. And it sounds like a description of a quark star is it has a neutron. It's like a neutron star, but has a neutron crust. But inside it, everything's just a quark gluon plasma. It'd be interesting to think about the decay of how quickly that quark gluon plasma cools down. Would it cool down, or well, here's the thing: strange stars are supposed to be. I heard this description of them being infectious, and like they touch anything that they touch turns into a collection of strange quarks. So anything it absorbs turns into strange quarks. It's a stable body of strange quarks. But I think it's more got a solid neutron crust. And then you've got the quantum soup of strange quark plasma inside. I think the neutron star crust prevents it. But yeah, I'm going off on a tangent here. But the only other place where you find a quark gluon plasma is right at this moment here. And this inflation field exists within the quark gluon plasma. And it causes the singularity to expand, not just such that the shape of it becomes flat, that everything within it retains perfect order, apart from these quantum fluctuations within the inflationary field. And it is because of these quantum fluctuations that gave shape to our universe, or that's how the Lambda CDM model argues it. I argue it very simply as our entrapped manifolds, space-time, our new universe, expands out and inflates out into our universe, into the larger superverse. But it is being fanned by the debris of the two neutron stars colliding. the debris of that, when you crack a neutron star open, as I said, got quark, is essentially quark gluon plasma. So you've got this lovely, that's where all the quark gluon plasma that came to fill the early universe came into existence. And it's what's like I'm showing by this red and orange plasma projected upon a grid. The grid itself represents the geometric shape of the entrapped manifolds. And here comes in, and in the making of this film, a discovery was made about the shape of kilonova. Actually, I've got it in my picture here. The shape of a kilonova is usually represented as being very asymmetrical. No, that's not there. Come on. Music. So this is an artist's impression of what a binary neutron star merger looks like. And the particular part I wanted to look at is how asymmetrical it is. So this has been done. This is not my artwork. This is NASA ESA commissioned. So it's professionally done. And you get the gravitational waves to merger, blinding flash of light, and from it you get this asymmetrical. Oh no, that. Sorry, I was looking. There's another animation where this is the resultant. You've got these two gamma ray bursts that are ejected because of the newly born black hole and the whole dynamics of the two rotating around, colliding. And so you've got this asymmetrical description of a kilonova. That's how it's been shown. Not the case. I'm the first artist that actually managed to get this artwork up. I had my explanation down and the artwork up in a matter of time. Changed all the other artwork around it. Another important thing that inflation theory has to answer is spherical symmetry. In order to derive Friedmann's equations of general relativity, of the cosmological solution, the FLWR metric, the F being Friedmann, in order for Alexander Friedmann to create a cosmological solution of general relativity which described an expanding universe, one of the primary assumptions he made was that there was this spherical symmetry. Or spherical symmetry is a requirement in order to derive Alexander Friedmann's equations describing an expanding universe. And then I mean, Lemaitre spends the first part of his book, The Primeval Atom, uh, essentially describing the underlying philosophy of why Friedman made the assumption that the expansion of a universe was spherically symmetric. Yes, so here we are. This is a paper that got published. One of the many observations that got published while I was making my film, and it really does change the entire course of it. I essentially created this whole new explanation to account for this sudden and to me this is observed. This is observed evidence that the explosion of a kilonova is spherical, has spherical symmetry. It is symmetrically spherical, which is a prerequisite for deriving Friedman's equations describing an expanding universe. And this is a matter of observation. Can the Big Bang Theory ever be created in such a way that it observes the scientific method? The answer to that question depends upon your cosmological principle. If your cosmological principle says that the binding principle of all things is that at the larger scales the universe is homogeneous and isotropic at sufficiently large enough distances, sufficiently large enough being somewhere in the order of 250 to 300 million light years. And the distance varies such that they can argue, well, the Boyer's void is not really statistically significant to be considered big enough. But the presence of the Boyer's supervoid is also part and parcel of what inflation theory is saying. So you've got this. So in the land of CDM model, standard model of cosmology, we've got this field that is responsible for expanding doing this very quick expansion, such as the universe is still homogeneous and isotropic. It's a mathematical hack. It's all a mathematical hack. That's all it is. Because they say, because when the LHC went looking for evidence of the inflation field, they found none. There's no evidence for it. So they say, well, the inflation field actually decays. There's another YouTuber, Dr. Brian Keating. His particular claim to fame is like, I nearly won a Nobel Prize. His claim was for his Nobel Prize was inflation. He believed he found evidence of the inflationary field within the cosmic microwave background radiation, but when his work was re-examined, it was found that well, actually, your readings can be explained by the presence of interstellar dust that was passing between the front of you and the microwave background radiation. So his observatories at the South Pole's looking out down towards the Eridanus supervoid, which is probably one of the most there's so many things about down that region. But yes, his claim to fame was essentially down at the South Pole. They've got the observatory, and he was one of, and he was trying to use pure pristine skies down at the South Pole to collect all these observations, but essentially some of those the observations from which he made his claim to say, I have found evidence of the inflation field from the cosmic microwave background radiation, were kind of essentially falsified by other astronomers saying, actually, your results are caused by interstellar dust, and so he kind of lost out on his chance for the Nobel Prize at that point of finding evidence of the inflationary field. So no evidence has been found of this field yet, but it decays, and then it's responsible for I think the way it seems to be the way it's formulated, the way they try and state it is the energy in the inflationary field decays such that it becomes dark, that which we call dark energy, and dark energy is collected like small soup bubbles. The soup bubbles these bubbles of dark energy coalesce together, and in between the filaments of the universe are squeezed together, and thus the cosmic web is actually born. Some of these voids merge into one another into becoming larger and larger and larger supervoids, such as the Boötes void. There's no evidence for this. Dark energy to me is mass energy density belonging to is that mass energy density that are belonging to objects of the superverse into which our universe, our entrapped manifold state based on we call our universe, is inflating into. And it traverses around these objects. Though I can't prove it for the Boötes void, when it comes to one of the local voids, here we have our universe, our galaxy, along with, here's the Milky Way galaxy, Andromeda galaxy, and all the local group flowing around the local cosmic void. This is another idea in cosmology called dark flow. It's its own entity that everything is being attracted towards the gravitational, what's called the great gravitational attractor, which is beyond the sight of our visible sight of the observable universe, beyond our event horizon of the observable universe, is this thing called the great attractor. Is there any evidence for that? Yeah. Our universe flows around objects of the supervoid because of the superverse. But here's what I think is my ultimate argument for the existence of the superverse, and that it obeys the same laws of physics, because our universe inherited its laws from the superverse. Our universe began as an entrapped manifold, as the ringularity sunk down after the collision of the two neutron stars. And then you've got this inflationary period this is my artistic inspiration of it. The two neutron stars collide, and the rotational black hole is born. So the ringularity sinks down and traps the manifold of space-time within there. And within that and then from that, the new white hole is born, and we have this new entrapped manifolds of space-time. They are, now here's the important part. Special relativity of the superverse. Our universe behaves in the exact same manner. General relativity applies. And so does special relativity. Well, special relativity says that the maximum speed anything can go at within our universe is the speed of light. Taking the same principle, fractal geometry is cosmological principle, and reverse is our parent. The expansion of our superverse, the expansion of our universe and our parallel universe of antimatter. The expansion is being restricted by the superverse's speed of light. So this can only so it doesn't matter. So even though the flow of space-time into the newly born black hole below the event horizon is faster than the speed of light, and coming up through the event horizon coming up through the anti-horizon on the white hole side, when coming up through that, it's got a rate of expansion that is faster than the speed of light below the event horizon of the white hole, but when it crosses that boundary, and you get this important dimensional rule swapping, the 3-dimensional time and 1-dimensional space then transform into 3 dimensions of space and 1 dimension of time within the entrapped manifold. But the expansion of this entrapped manifold, even though it's being fed by by an outflow moving as being effectively it's effectively the most concentrated mass energy density, namely quark, gluon, plasma, and then that comes into this entrapped manifold. It really wants to expand and wants to expand at the fastest possible rate, but it is constrained. That's the important part. It's constrained. It's constrained by the superverse's speed of light limit, because it's obeying the rules of special relativity. You've got a speed of light limit of the superverse. Now, whether the superverse's speed of light limit is exactly equal to our speed of light, that becomes a new philosophical question. I would say the superverse's speed of light limit is equal to the speed of light. I did a lovely animation of it. I've done so many lovely animations of so many things. Sort of here, flat grey. This is where I've got some nice ones sort of describing general relativity. So here it is. So, in general relativity, if our sun was suddenly removed, would the Earth know about it, or how long would it take? General relativity says, well, the rate at which it would take 8.5 minutes I think that's the time it takes for light to travel from the sun. It takes 8.5 minutes for that information that the sun has suddenly disappeared suddenly get to us, and the consequence being, well, there's no sun anymore, so I'm not going to orbit the sun and just fly off. The rate at which information moves across about about the curvature of space-time. The information that our sun is gone. It takes 8.5 minutes to travel across the gravitational field. My philosophy says our universe is made up of the electromagnetic field being of the superversity's electromagnetic field being torn in two, and that's where our manifolds come from. So our electromagnetic, so what is to us the gravitational field, or the curvature of space-time as we know it in our universe, is also the electromagnetic field of the superverse. And one of the prime reasons for saying it is like, got my phone here. I can't put my hand through a phone because it's a solid object. Most of that's free space. Most of that is is free vacuum. There's no the Rutherford experiment showed just how much free space there is, how much space a nucleus occupies, and how an electron occupies. My hand should just move through this, but it doesn't. And the reason it doesn't is because electrons repel. Electrons repel from the electromagnetic field. It is because of the electromagnetic field that gives any object its resistance to being passed through. Gas, liquid, they have gas doesn't take. Well, if you're going at Formula One speeds in a racing car, you're going to have, or going hypersonic in a fighter jet. There, you're going to have resistance problems of gas. More so when you're trying to swim through water, you meet more resistance. And then third state matter, gas, liquid, solid, I can't put my hand through it because of the electromagnetic field. Just as our universe flows around the volumes, the gravitational field is flowing around these solid objects of the superverse because it is because what is to us space-time is the torn electromagnetic field of the superverse. So that's my general thoughts on like how am I defining special relativity and general relativity, particularly the special relativity argument, because the expansion of our universe is constrained by the speed of light of the superverse, which I just think is, as I just said, is like the speed of light, because specifically of this particular argument here, where if you take away the sun, it takes 8.5 minutes to travel across the curve, or the change in the space-time curvature, that change to reach us, and at which point Earth flies off into the void of the universe, because it no longer orbits the sun, because there's no longer the curvature of planet. But the important point is that the expansion of our universe is constrained. It's constrained by the speed of light process. Actually, got a number here just showing the general principle of it. But into this curvature, and this is flat up here, the curvature of space-time is flat up here. It's not down here. So the two neutron stars, as they come in, the gravitational waves that emanate from them, or I should say super gravitational waves, but effectively it's the exact same pattern happening irrespective of scale. And so our universe can expand. So I've got our two. So I've got firstly the expansion of both universes, or both entrapped manifolds. So here, this is our early. Say we're an observer in the superverse, and this is our early newly. This is our newly born universe, or a newly born entrapped manifold of space-time. And here, we've got this newly born entrapped manifold of space-time. Born, one going this way, another one going this way, which is CPT symmetric. The conclusion, the CPT being charge parity time symmetry, but that's not an argument itself. For that particular argument, see the CPT symmetry here. This needs to be, though I'm currently thinking about redefining this whole thing about pair instability supernova and baryogenesis and more arguments I've got to get, and I'm currently working through, because everything is just falling into place here. All these little parts, and this is one of them. This spherical symmetry, and it's spherically symmetrical on this side and this side, because initially it is being constrained in inside the superverse by the speed of light, and then falling through self-similar patterns repeat irrespective of scale. Kilonova, an actual binary neutron star merger that was recorded, observed. Everyone saw it. We saw the gravitational waves coming in, and then every single astronomical instrument went searching for it. So the amount of data from an observable binary neutron star merger upon which I can actually build my testable hypothesis, and this is one of the ways it's being tested. Well, I've got spherical symmetry now, and that's required to give me Friedman's equation, to derive Friedman's equations describing an expanding universe, which is fundamental to Big Bang Cosmology 101. It's in George Lemaitre himself. Chapter 1, spherical symmetry, importance of it. And that, such that you can say in the second chapter, well, got spherical symmetry as our principal assumption. Of course, this all happens while I'm making this film, that's just like one thing. That's just one thing that happened. Never mind boat, brightest object of all time. Then there's the April Fool's little blazar. I'll never get over my. I will never get over. I don't even. If you ever manage to actually make it through what I've got, I mean, actually, this film is not even finished at the moment. I uploaded it to like, right there's at least something definitive. But so I've got down to this point here, and I've still got to, like, more or less do all. So by this point, I'm realizing a couple of things. One, this film is so dense in so many places that it needs to be broken up into bite-sized chunks that are far more manageable, or I could just continually vlog and keep reiterating all my various arguments over and over and over. I think it requires both. Um, but in terms of like, how do I could do one episode? Why is the universe flat? Why is the universe requiring spherical symmetry? So these are two very important things that allow me to come right down on top of inflation theory. Another argument that I'm just gonna find these are really the animations, I think. So this one is showing that flow of space-time is down in towards the singularity, back up out of it, and that the main direction of travel out into the universe is in a unidirectional manner. Of course, what is the evidence for this unidirectional manner? CMB dipole. So here's another argument. CMB dipole, which essentially shows that the universe, of all the signals in the microwave background radiation, this is the strongest. The temperature fluctuation of the CMB dipole, I think, if I remember off the top of my head, I thought I saw a quote saying it's 10 to 18 times greater than all the other temperature fluctuations within the microwave sky. So this is the biggest signal of what the microwave sky is, or what's happening in the entire universe. The counter argument, Lambda CDM model, and what theoretical cosmologists have been saying for a long time, and saying like, no, this is due to the CMB dipole is due to how the Earth and the Milky Way move are affected by this great attractor and essentially moves towards the great attractor. And because of this movement towards the great attractor, along with how Earth moves, along with how Earth, the solar system, moves through them and around the Milky Way galaxy, is the result of the CMB dipole. I use those the cat-wise quasar groups observations of this, and the respected repeated reproduction of the independent reproduction of their results, saying, look, no, the CMB dipole, this Doppler shift explanation, it does not work. It is not what we are seeing. It's failing the scientific test. That's one of the arguments I laid down on the CMB dipole. Sorry, I was explaining the spherical expansion of the unit, the spherical symmetry, and yeah, here's another example of like why I just call my thing inflation killer. I've got flatness, I've got spherical symmetry. Of course, one universe will rebound off the other. So although these expand, they're expanding at this rate, they're expanding at the speed of light at this point, and because they're constrained by the subversive speed of light, just as a pair of subvertices being born inside our universe from the binary neutron star merger is going to produce something that is spherically symmetrical. And the other great thing is that, as I was showing you earlier, the artwork is asymmetrical, and And to summarize, is this part here. However, an additional process seems necessary to make the element distribution uniform. The element distribution, as I was showing earlier, I basically summarized with this animation. So you've got all the elements either being eaten by the newly born black hole, or they're being pushed aside because this is the electromagnetic field torn apart. So there's going to be interaction with atoms. This has solidity. Well, certainly it had solidity at this point because it was being driven by great amount of mass energy density. At which point we're calling this dark matter. At which point we're calling this dark matter. If it's entrapped inside our universe, that's how I get to dark matter. Very simple. But the elements are being swept aside to have this spherical, symmetrical distribution, which is then observed I mean, as I say, this is observed. So, yeah, got so coordinate flatness, spherical symmetry, CMB dipole. But there are those large-scale anisotropies. And those large-scale anisotropies, as I say, are coming from the gravitational waves of two neutron stars as they come in towards another. So this is just before they collide. They tear each other apart and start to create this cylindrical solenoid, what I would now call a blitzer. This thing produces fast radio bursts. So that's another new thing that came along while I'm putting the. I didn't even finish recording the audio on some of the stuff, and like a new discovery. This is one of them, particularly being this identifying a binary neutron star merger as being a source of a particular very fast and energetic fast radio burst. And usually fast radio bursts are thought to be something that can artificially be created. It's not something you find in nature. It's something that requires intelligence, humans, aliens. It's thought to be a signal of extraterrestrial life for a long time. Fast radio bursts were thought to be that, but this solenoid, this nature's ultimate dynamo is being born here. But you've got these gravitational waves that are also emanating out. These gravitational waves, in our universe, we observe them with LIGO. And so, you've got the expansion of our early universe with spherical symmetry, and it comes down and meets its antiverse, rebounds off it. But at this point here, the curvature of the universe in the southern hemisphere is being manipulated by these super gravitational waves of the superverse. The shape of our universe is being shaped by these super gravitational waves, or the shape of a subverse being born from a binary neutron star merger inside our universe is also in turn being shaped. So I've got a couple more animations. So the argument I put together is as one gravitational wave pushes up such that So you've got the gravitational wave here, and the gravitational wave bends the curvature of space-time up and over it. It pushes the fabric of our universe up. And so I'm showing the distribution of matter inside our universe. And watch it go from its initially homogeneous anisotropic mixture anything within that volume is now being pushed aside. And so as the gravitational wave comes down, as our universe effectively comes down and rebounds off the our parallel antimatter one, not shown here, just to show you this one. So you can see the curvature imprint. Here I'm showing this curvature imprint coming up, and it creates, because the matter is pushed aside from the one that came up from the blue gravitational wave, it gives us an area that's got less mass energy density in it, and thus is much cooler. And so this blue gravitational wave is responsible for this blue spiral arm on the microwave background sky. Now, vice versa, do the other argument. If the phase of the gravitational wave is in the downwards direction, so that's what I'm representing with this red gravitational wave. So red and blue, red to signify what causes the hot arm, and the blue to signify what that causes the cold arm spiral in CMB. Well, as it comes down, it creates a trough, and within this trough, you've got this new volume of matter being filled up very, very rapidly with the quark gluon plasma. That's kind of starting to cool down a wee bit, but this is the very early stages of the Big Bang Kilonova, and this is filling up. This fills up with a larger density, such that the density of the distribution of mass energy density here is much greater than it is on the other side of it. So I'm trying to show what the gravity, how the mass energy density is redistributed within the southern polar hemisphere as our entrapped manifold of space-time that is our universe prints down onto the super gravitational waves of the kilonova event, and then come to form both this cold spiral along with its hot adjacent spiral on the cosmic microwave background radiation. So, with one explanation, I'm solving a flatness problem, why the observed problem, why the universe closed. The expansion of a kilonova inside our universe, giving birth to a pair of subvertices, and using it to explain Friedman the necessity of spherical symmetry, of how spherical symmetry inside my Big Bang Kilonova hypothesis model. Where is that coming from? In fact, it's answering the exact how and why there is spherical symmetry in the early universe. And it is because it is expanding into the superverse. And the superverse is constrained by its own speed of light limit. And that's it. The special relativity of the superverse. Because fractal geometry's cosmological principle and self-similar patterns repeat irrespective of scale. Then I explain the CMB dipole with it. And then I use it to explain these large-scale anisotropies. CMB dipole and large-scale anisotropies. Landis CDM model doesn't even attempt to answer these questions. It doesn't even attempt to tackle them. I've got them tackled with one answer. And this is my answer. The current plan forward for me at the moment. This film, if you actually make your way through it, such that I am showing these arguments, you also see I'm counting on a number of highly improbable events that are sort of just happening around or just happening within astronomy and in my personal life. It's just like, hey, that's fun. I've ripped apart that one. But yeah, but as part of this that I've now got to complete the film, because it really all comes down because there's a little thing at the end of my film which is like, well, I've got to pay tribute to that which is my artistic inspiration, that which gives me my logo. And I'm beginning to consider handling the Holy Grail is like handling a nuclear bomb. Be very, very careful how you go with it. I'm just wondering what new thing is going to blow up in my face. Or water. Well, at least I will hopefully get the internal plumbing of my house sorted out. If you're hearing banging going on in the background, that's what's currently happening now at the moment. But yeah, I've still got to complete this film. But more specifically, I've got the essential basis for my argument through and through. I thought I already had a very, very strong argument of all the other things I put up against it. But like I say, I'm just calling this inflation killer now. It answers the hows, the whys. Why is our universe flat? How did our universe come to have spherical symmetry in it during its early expansion? Got those. Why is the CMB dipole the CMB dipole? What is dark energy? What is dark matter? Why is there no dark energy at the time of the last scattering, of the recombination of the microwave sky? There's no dark energy measured there. But yet our galaxies, our universe is composed of 75% dark energy now. Where did all that come from? Questions that the Lambda CDM model fails at. And one explanation I've got, well, like I say, I've got the large-scale anisotropies, and I don't just go into large-scale. Oh, hey. Well, there's two types of large-scale anisotropies. There's the low dipole ones, like the CMB dipole, and here. But I use this as. But here I'm showing a CMB dipole against a galaxy spin of asymmetry dipoles. So this is another map of a cosmological feature, the asymmetry of spiral galaxies. That also matches up. Here's something that's definitely cosmological in distance, being matched up with something that's definitely cosmological in distance. Same here. Where did this quadrupole come from? In fact, what gave shape to the L equals 3 quadrupole, and with its second harmonics repeated in L equals 6. Where did they come from? Though that's an entirely different matter in that I argue, one of my main arguments is that the octal map is a signature of the ringularity itself. So this particular one is showing the entrapment of different parts of space-time: black hole, wormhole, white hole, newly born universe. But where was it? I was looking for essentially, yes, what caused these, and the one where yes, that ring. Effectively, looking at it from another point of view, if you consider this the fabric of our superverse, it gets pulled through the ringularity. The imprint of the ringularity is going to imprint itself. So the ringularity was what I was showing in the other animation here, where you've got this point of infinite curvature, or the two binary neutron stars collide, and within the heart of the blitzer, the matter collapses down into a ringularity as soon as it forms as ringularity. As soon as it falls below a critical point, that point there is when the black hole is born. But my other argument is that you've got these other entrapped, because of rotation, you've got these other entrapped points. It's not this, the singularity would dumps this point down, the point where red is. It would pull that down towards infinity, whereas this is being pulled down towards infinity. But I don't actually use infinite curvature. I more use Nikodem Pompolomsky's work, which factors in the torsion metric, which stops us collapsing down to infinite curvature. So I'm using that particular mathematical description, and it's rotating. So we got below the blue part, that's the black hole, and then into the green and round the ringularity, you've got the wormhole, and then you've got the white space, which is the white hole, and then you've got this new red part that's still above the critical limit. And that new part, and so one of the things I'm trying to show here is, like, as the ringularity sinks down, you've got this part in the middle that's always going to be above it, or is going to be very quickly filled up with all this quark gluon plasma. Now, it's not just quark gluon plasma. It's fragments of the super neutron star itself. The most heaviest matter known to the superverse. Fragments of a super neutron star. Or rather, supermassive black holes. Where did all the supermassive black holes come from? They are fragments of the neutron star of the superverse being torn up and fragmented. That's what all these white and blue particles are here. This is your quark gluon plasma, but this is all your particles of the superverse coming, or these. I mean, a cube of neutron star matter inside our universe, and from a neutron star inside our universe, weighs 1 sugar cube is equal to the weight of Mount Everest. You take all of Mount Everest, its roots and all, Shrunk that down to a single sugar cube. That's what a neutron star, single sugar cube of a neutron star is. That's how insane neutron degenerate matter really is. But if you've got all these fragments and they're coming in and they're causing the inflation, being pushed up inflation of our universe, then that's where my answer to where did the super black holes of our universe come from? So it's a neutron star particle. It's what's left of the neutron stars, and each one of those particles in turn enters our universe from the very, very moment and very beginning of expansion. And each one acts like a seed around which all the other around which all the other quark, the cooling down, the quark cooling plasma cools down into effectively ionized hydrogen gas. Protons cools down, protons and neutrons form, and electrons form, and within the plasma of the hydrogen plasma, that starts to coalesce immediately from the moment of creation, immediately around the newly born supermassive black hole, or the fragmented particles of the superneutron star each one of those becomes the supermassive black hole inside our universe, and around which the hydrogenized plasma swirls and forms and causes. And then I make the same argument. These supermassive black holes begin to feed. These supermassive black holes inside the quark gluon plasma. We've got an accretion disk around which is so it gains its accretion disk of hydrogen plasma from the very beginning. The background here is the hydrogen plasma, and the supermassive black holes feeding, and the same thing is happening. A pair of subvertices are being born. These subvertices grow, spherical symmetry, same argument. But here I'm not. Here there's no gravitational waves, but because they expand and then expanding all directions, pushing down towards each other. They push down towards each other, flattening the material in between into becoming an even thinner accretion disk, and then expand outwards. And so you have a spiral-armed galaxy being surrounded by halos of dark matter from the very moment. So again, same argument, exact same argument of entrapped manifolds of spacetime being used to say this is how spiral galaxies are born. Of course, as our elliptical galaxy, of course, it's like, how permeable is this? Well, I think it's not so permeable when there's great amount of mass energy density in here, like right at the moment of the Big Bang Kilonova, or right when these two start to feed and effectively you've got a bunch of quasars. But effectively, I'm using the exact same pattern and argument to explain Big Bang, galaxy formation, and stellar black hole formation in our universe. Particularly this, and most particularly in explaining this, because no one's explained that. But no one's also explained why the James Webb has picked up spiral galaxies coming from the time of the Big Bang. These massive galaxies are around 5 to 600,000, 5 to 800 million years after the Big Bang. That's the estimate, based on the redshift of these particular massive spiral galaxies. Where did they come from? How did they get into place? Well, I've just given you my answer, and it's the same answer over and over and over again. So the number of questions I am able to answer suddenly with just one hypothesis is, I guess it's to be expected when you've got a blitzar happening on top of your arse on April the 1st, and you're wielding one philosopher's stone in one hand, and I'm bearing down on the seed of life in this one, particularly the octopole maps. But I won't spoil the ending of this particular film. But I think I'll leave it there for today. Other comments is like, I don't know, I believe that film, and it got like, I mean, compared to any of my other videos, 26 views, 73, 21, it's like a 1.4. Like, oh, I'm pleased with that. That's a good result. But yeah, I think at this moment now, I'll finish this actual film off and actually probably watch the complete film. Then I've got a lot of tidying up to do on my website. This reacts to mouse events. This doesn't act to touch events. Whole front page needs to be redone. I don't think I should be so. Part of me is like being really aggressive towards the Lambda CDM model at the moment. Well, I'll put it like this. The whole process of this. Why is the universe flat? That's a question. Why is the universe homogeneous and isotropic? There's another question. Physics is all about answering questions. I mean, and as you've just seen, I've been going through my one explanation, answering multiple questions. That's the strength of my hypothesis in its current form. Answering multiple questions on every single front. Answering the questions that inflation theory couldn't even tackle. And inflation theory is completely made up. It's completely theoretical. They've got no evidence for it. That's what I love about the fractal geometry being a cosmological principle, because self-similar patterns repeat irrespective of scale, and I am able to create a testable hypothesis about the Big Bang. If a kilonova is not doing it, the Big Bang's not doing it. If the Big Bang's doing it, the kilonova is doing it inside our universe. And I've got that. I've got spherical, so that, when I say I've got that, that's like, what's that additional process? It adds up and adds up and adds up. And as I say, cosmologists have not been thinking about this. I'm the only one that's doing it. Or, if you want to join me and start thinking about it yourself, and please be my guest. There's so many questions to answer. So much work that has to be done. The first part of that work I need to do is take this and put it into a proper peer-reviewed format. So that's essentially, this is what I would call the sterilization of my current work, because there are arguments that I'm making that I think are just falling on deaf ears at the moment. It's like, do you know what the symbol is? Do you know where it's coming from? Take a good look. Go look. I mean, when I say it's coming from here, it is the thing that comes from the quest for the Holy Grail. Here's my path towards it. Here's a whole lot of curious things that have happened since then. And that's just adding to the list upon the. But this thing here, well, this guy is famous for one thing and one thing only. I don't even want to touch that history with a barge pole. Like, what the hell are you supposed to do with that? But, oh, I know exactly what to do with it. I know exactly without a hesitant moment of doubt of what to do about it. And that's not very good. Screaming heebie-jeebies for no. But hey ho. You got Philosopher's Stone in one hand and the Holy Grail in the other. It's to be expected. And that is to be expected. And that's why I went with the. That's why I went with. I think it was Pascal's Wager. I think Pascal's Wager, I turned out, yeah, so there's a god. And he pulls April Fool's jokes on you. While throwing several Death Stars at you. There's a boat, brightest object of all time. That's all parents to build supernova stuff. That's worth an entire film in itself, because that's baryogenesis, matter, antimatter. But yeah, self-similar patterns repeat themselves even at the human scale. And that's what the end of the film is going. That's the part that I've got to pay attention to, because there have been some particular instances about well, between the time I'm making this film and getting it done where I released it there, well, on one of I've got several new sacred pieces. One of them being the essential essentially the floor of the altar of the Chapel of Westminster, upon which the Queen, which back in October, the Queen Elizabeth laid in state at her funeral, and then we saw just earlier this month King Charles III being crowned on top of this one particular floor, and if I could sum up the whole purpose of this entire film, it's to kind of say, look at the sacred geometry. You know that imprint there? The imprint of actual which, in terms of the physics, looks like this. Which is rotating Bose-Einstein condensates, like rotating liquid helium. But this is particularly quantum irrotation. But you also get quantum irrotation inside the heart of the ringularity, and the whole napkin cloth ringularity argument is sort of central here onto the octopole. Like what formed these? This is the mark. These and the L3 and the L equals 6. That is the mark of quantum gravity. It's also the mark of entire creation. 6. 2 divided by 3. Spin of a quark. Top quark, I think. 1 divided by 3, spin of the other type of quark. Up, down. The spin of all the quarks. There are 1/3 to 2/3. Spin of particles, half. 1/2. So effectively, in there you've got the numbers 1, 2, 3, all common one. Single common denominator is 6. And there are 6. And in fact, we're saying like the seed of life symbol, flower of life, that is the very element that builds our reality. That in there is the mathematics that we've been that humans have been doing since the time of the Egyptians. So I've got a particular Egyptian engraving on, I think it's in Temple of Osiris. That is like, but it's also my personal like, I suppose personal pilgrimage to various sites where I found the seed of life. One by accident, and 2, I need to take a camera down to the Westminster Abbey now just to get the footage for the end of my film. I wonder what's going to happen down there. I hope someone doesn't go nicking my earphones. That's what happened last time. That's what happened a couple of weeks ago to me. On a religious temple site, someone goes and nicks my headphones. Of course, I do like I do have a bit of a thing for audio, being the one audio player that is actually linked to the Big Bang Kilonova Hypothesis, my audio player. So, what came before the Big Bang Kilonova Hypothesis? Black Omega. My one and only thing I worked on for many years. I actually still want to work on it. I want to really get the DSD audio implemented in this. How can I call myself an audiophile if I don't have DSD audio? Anyway. So yeah, these are. So I visit a religious site to get seed of life symbols from a Hindu site. Someone rummages through my backpack while going up. There's a huge bunch of stairs going up to it. And some nabs these headphones that I just bought, and they're super geeky headphones. Like I've gone through this is like random shop in Kuala Lumpur that I came across that just like, oh, this is audiophile heaven for anyone who likes headphones and needs the latest audiophile gear. Here, oops. Such a type of headphone was sort of this kind of headphone. The in-ear. This is supposedly the world's first lithium driven one. Oh, I went back to the shop to replace the headphones because it was 1, my birthday, and 2, there's always a price when you come against true divinity. I always find there's a monetary cost to it that I pay down. Doesn't matter. Don't really matter. Doesn't really matter to me. Because at the end of the day, hey ho, I got there first. But it's not part of it. It's like I managed to cross the finishing line on this and so many things. I know what I've got to do going forward, but it's not part of it. It's like I want to concentrate on something that is not something that's more down to earth, more like. Well, I'm going to stop it there because I just could hear my shower. The whole plumbing system is currently being repaired in the house. Part of yet another long-going saga here. Some of which you there was that part and there was that part. Some of which you can read about here. Some of the ongoing plumbing catastrophe. It happens. And if you're wondering why is my hair a bit greasy, or been greasy in most of my vlog videos, it's because of broken shower. That's a shower being repaired. Anyway, catch you next time, and well, hopefully see you soon. All right, cheers. Until next time.